let me come to our next speaker. It is Hassan Hamdoun. Hassan has obtained his PhD in advanced telecommunications from Swansea University. Could we please
Swansea.
Swansea.
Yeah.
Where it is?
It's in Wales.
In Wales? Ah.
Yeah.
I didn't know. Yes, in Swansea University in 2013, and he holds an MSc of Sheffield University in electronics engineering. He's currently a senior researcher in video delivery research in BT. Prior to BT, he was at the University of Aberdeen as research fellow. Now I come to his hobbies. It's interesting. His hobbies include racket sports, football, reading, and traveling. I suppose he must have a lot of spare time.
Yes.
And the next interesting point is he enjoys organizing events. What a pity that we didn't know it before. Maybe he will help organizing the next FITCE Congress. Walter and José, you know, he have a helper. Yes, I will come to his presentation. The message of his presentation is HTTP. It is a hyperlink transfer protocol solution for the future media delivery. Mobile networks, especially 5G, will be able to deliver media in an efficient way. His presentation is media delivery in 5G. You have the floor.
Thank you. All right, thank you for the introduction. I have the pleasure to speak to you today about media delivery in 5G. So I'm in the right session. So Andy have introduced quite a few things on the architecture of 5G and how the control user plane separation is important. And Juan also gave us a very interesting techno-economic analysis. So I'm going to focus on what aspects of the architecture and functionalities needed to provide broadcast and multicast in 5G. And I'm going to try and do that from the content service provider perspective. So that's slight deviation to the network side. Okay, so slides don't move here, but they move there. Interesting. So I'm going to talk about the vision for unified media delivery, and then move into how that the current 3GPP activities into the delivering of multicast and broadcast content, and finally discuss what challenges we still need to resolve to enable multicast broadcast in 5G. And I will conclude with some recommendations and architectures to use. All right, so this is a view of the current media delivery today as we see it: mobile operators, fixed operators, and content service providers. So we have got the outside production that's Jamie talked about, and then we have 4 routes. We can go through satellite, terrestrial, or multicast, and or ABR, that's HTTP based. And the delivery is usually through a satellite set-top box where you use MPEG-TS, or a terrestrial network that goes into the set-top box that we connect to our TV, or as we do it in BT, we do it through IP. So we have IP multicast, and we deliver IP to the home gateway that's delivered to your set-top box and you watch on your TV. And that there is a mobile side where we deliver over LTE and 5G. So what's useful in this picture, and also challenging, is the amount of formats that we need to deal with in a converged fixed network scenario. So you on the satellite side, we need to deal with MPEG-2 interlaced, H.264 interlaced, DVB CSS. On the fixed IP, we need to deal with all those. There is also a lot of developments in the dash side of things and HLS. On the mobile side, it's a slightly different picture because mobile only support progressive video. There is no interlaced anymore. So that's a technical format difference. And in all this, we have different unicast and multicast routes you could see there. And we have always interaction with the CDN where the content is hosted. So just keep that in mind as a general architecture. So given this converged architecture, and we want to deliver video, according to Cisco, video is 70% of the content that's been delivered in 2017. So what are the video requirements? So we have timely delivery, and we need to match the bit rate to the media. So traditionally, what we do as a broadcasters, a network service provider, is that we use RTP, real-time protocol, because it supports that. And we use network quality of service on top of that. RTP helps because it gives us the bits, the timestamp, so we can monitor which packets are lost and we retransmit them. But that's actually not how we do it over the internet nowadays. We do it over HTTP. So why is that? I think that's an interesting takeaway maybe we need to take from my presentation is HTTP supports delivery times are highly unpredictable because it is based on the transmission control protocol, requires acknowledgement, requires congestion, monitoring of the congestion window, and a lot of variation in the throughput there. But we still use HTTP. So what's going on there? So there is a conclusion from that, which is that HTTP is a success, but it's a success even though it's suboptimal for everything. It's quite suboptimal to use, but it works. So that's one thing. And HTTP gives us a very important interaction or interface point to the content service provider because it's provided a very simple interface between the content service provider and the network service provider. That's why the HLS and the dash are quite on the rise for media delivery nowadays. And if we expand this a little bit and look at the end-to-end architecture, so we have the content service providers, that's the CDNs, the content service provider, so the Netflix and the Amazon. We have the CDNs, that's the Akamai and the Limelight. We have network service provider, that's BT, and then we have an end user. So what we currently do is that we push content from the content service providers through the CDN and delivery over unicast to the BT home hub, which you connect through Wi-Fi to watch your videos. But this is not very optimal because you need to send to every single user that YouTube video separately. And there's other things that we, the EE, the mobile arm of BT, has been seen in the network. So this is a graph which shows the SGI band. That's SGI, that's the link between the mobile network and the data network, the outside internet. How the capacity changes during those content storms, those high demand periods. So this is during Sunday of the England versus Sweden, Russia, Croatia, compared to the previous Sunday. There's quite few. This is a content spike at a span of 2 hours, 1.5 hours to watch the game. You can see the same on the EE network during the England-Wales football game in the Euro 2016. And also you see that this is not, it's across the devices. So there is, this is accessed by concurrent devices at the same time. So you see here the peak of the unique devices connected to the network at that time during the match. So all this makes the unicast no longer, or a very costly solution. So because obviously you need to increase your throughput by 1,000 times probably, and you increase your the number of devices. Obviously, the more devices you have, the more signaling in the core network you require. So this is the view for the multicast proposal. So that's you do instead of sending unicast, you send multicast. But multicast on its own is not optimal unless the content sits at the edge. And Andy mentioned this as well in his presentation. You need some sort of edge edge caching. So you need to find the trade-off between what do you cache at the edge and what do you keep in the core of the network, in the CDN. So now this is the vision. We want to reach this, but we want to do this optimally and want to do this within a 5G network. Now what the 3GPP is doing about multicast broadcast implementation as a technology within the 3GPP. So this is an architecture of the LTE EMBMS, that's the Enhanced Multicast Broadcast Service. So that's the 3GPP LTE solution for delivering multicast that, as we see in the fixed network, to mobiles. And the network is basically a standard LTE network with the yellow bits added. So you need a multicast service gateway. And that's essentially what delivers your user plane multicast packets to your UEs, and also perform the session control with the MME. MME is basically what provides the signaling and session control in the LTE network. You also need a BMSC, that's a Broadcast Multicast Service Center. So that's what interfaces the LTE network with the content service provider network. And interestingly, the 3GPP defined an interface for that, which is very rich for the use of the content service providers to enable the ingestion of content through the XMB interface. You also need stuff on the run, obviously, to deliver the same content to all the mobiles within the cell. You need synchronization. And that's why there is a sync protocol there in red. And this is a multicast service edge. That's essentially an optional feature you can implement in the eNode B, the radio, or you could do separately. There is other bits that's added by vendors, like Nokia added a bootstrapping function, which provides more of a content discovery method for discovering that content through bootstrapping. But what you could take away from this slide, that 3GPP have in the LTE release 8 and 9, and up to 14, there is a way for the content service provider to deliver similar multicast IP to mobiles. But there is some things you need to take away. 4 things, actually. One is that 3GPP had make it easier, standardize a way of mapping between the cell ID, the geographical area you want to cover, and the cell IDs of those hexagonal cells that you want to tag the mobile for delivery of broadcast. So that's what they call the single frequency network area. And it's up to the content service provider now to come up with ways of doing this. Now that's where innovation comes. There is a standardized interface. It's a RESTful API, so you could go and develop software that's sort of retrieve what information is delivered in broadcast, what else you need to add, how many users, etc. The multicast content can be accessed through a URL, so it's similar to HTTP unicast through a session description protocol. The details of that is a bit complicated, but you have a session description protocol for media ingress through your contents through this XMB interface. Usually, Flute is standardized. That's a transport protocol for that, but it's not HTTP based, but it's a way of delivering. And there is evolution for the radio access network based on this. I'm not gonna delve into. Now we have this as a baseline, but it's still not clear how to do the multicast provisioning in the core. The RAN is there. There is some limitation in the RAN. You can't cover a very large area. Still, you could do up to 10 kilometers. BSPs wants up to 60 kilometers. So there is still some stuff to be there. I have them in my backup slides. I could bring them up if there's a question about that. But I'm going to go very quickly across the next one because they are basically some technical reports which specify requirements for multicast broadcast. And I highlighted, underlined the key things. So there is something that called, you can actually, 3GPP wants to have a channel code for a cell where UE could tune into. So you tune into channel number 1 to watch BBC on your phone. So that's something cool that you could do. There's also requirement to support lossless 4K, support multiple quality screens. There you could do ad hoc broadcasting where you could actually, another mobile, another UE in a different cell want to broadcast something to you in this cell rather than the BSP broadcast for you. And there is good requirements, there is keen requirements to do transparent multicast. There is numbers against what UHD and HEVC to use. There is requirements to do a downlink only broadcast similar to the way terrestrial broadcasts work. And the list goes on. That there is specific requirements on how many channels and which data rate and which area to cover and transition between a DTT coverage to a small coverage, extending the coverage to the countrywide, all that. And there is also discussions currently on the mixed mode broadcasting, which is you switch between multicast and unicast based on the user demand, which is very appealing to content service network service providers. So now, how to do that? So this is the same, that's what Andy showed, that's the service-based architecture for 5G. And that I brought this up just to say, this is this is based on the CUPS principle, the control user plane separation. So this is the user plane. So if you want a unicast, you go through this route, you go to your RAN. So basically, you do this, you do the authentication to the AMF. The AMF finds the SMF. The SMF set up your sessions, finds the UPF. The UPF assigns your IP address, and then the UPF set up your user plane session. Here there is very nice. I highlighted those two, the PCF and the NEF, the network exposure function and the policy control functions, because in my conclusion, I'm going to say something about them. So essentially, because it's a service-based architecture, you could discover services between the elements in the 5G core using a request-response model similar to HTTP, strikingly, or through a subscribe notify model. So the network exposure function allows you to do that. The policy control function is very important because they allow you to set your policy for charging and policy for delivering the content. That's very relevant to the content service providers. But all this is currently unicast. Now, how to make it multicast? We need to do the RAN first. So the RAN is not interesting to anyone here. So I'm going to this is how unicast is delivered. So basically, you multiplex your channels into a shared channel that everyone sees. So when you access the cell, all of us here come to the same cell. We're all sharing the same PDCH, basically, the capacity of that. In order to improve it, you come up with new channels that support multicast, and you add them to that downlink shared channel. So now you can do multicast and unicast at the same time, but that's not enough. You want to do multicast and broadcast alone, dedicated. So what you do, you have new channels, multicast common control channel, multicast traffic channel. You multiplex them into multicast channel in the transport layer. That's a MAC layer. This is radio link control layer. This is MAC layer, and this is physical layer. And then you have a dedicated physical multicast channel where you send your content. And this is downlink only, no acknowledgement, like TV. If you didn't receive it, you missed a packet, it's gone. You move on to the next packet, basically. So there is application layer for error correction in there to correct for errors. So there is no retransmissions at all. Now, how to do this? Because HTTP is very synchronous, so we need a solution to receive. How many much do I have?
2 minutes.
Okay, I will try. So yeah, you need to receive everything synchronous. You receive a synchronous request, but you need to come up with a synchronous way of responding. So that's how you do it. You aggregate your responses. I'm not sure if that was clear. And then you deliver them at once. So this is a proposed architecture for media delivery in 5G. I'm going to try in 2 minutes to summarize what I think is missing there and how this works. So you prepare your content. You have a controller which basically do all the redirection and request routing. You have your content origin there, which now supports unicast origin and BMSC. I showed there for the EMBMS. You have a delivery code that's basically a mid-tier CDN level. And then you have your actual edge delivery. And what happens here is that this architecture now fits into the previous MBMS architecture I showed through the MBMS gateway, and uses the same core, 5G core, with all the nice features of the session, AMF, and PCF, etc. And there is new things that we could do there. We could assign certain new CSB world features and map them into this architecture. So we could say we want a DRM license server, the digital rights management, and we can do that in the application function or the application user service function. We want to do quality of experience reporting. We can do it as an AF function, etc. in the interest of time. So, and based on that, there is 6 different ways in which you could tailor the architecture to media delivery. So you could follow the EMBMS one with what they call MOOD, that's multicast operation on demand. You can switch between multicast and unicast. You can implement transparent multicast based on PDU session modification. You can have a separate broadcast carrier for 5G, for multicast broadcast. So for example, BT can have the normal LTE on frequency 1, but have multicast broadcast on frequency 2. You can have an architecture based on point-to-multipoint services, and you follow this media delivery that I showed, and you can have a receive-only mode where the user, the mobile, my mobile is there, doesn't have a SIM, essentially hook to the network without a SIM and start receiving linear channels. So that's partly that's in the standardization by 3GPP, and there is ways you could use that within this media architecture I showed. And there is some activities in the standards. 3GPP, also there is multicast APR stuff. In DVB, there is a quick standardization that's relevant to the discussion by IETF. So my summary is all those points, if you want to read them. So HTTP is key, and it will be key in delivering multicast content. So there is ways of making HTTP, moving HTTP from the unicast world to the multicast world. The 5G system architecture is flexible because of you have the PCF, you have the network exposure function. Now we can talk about slices for delivering multicast broadcast in 5G. I think that's pretty doable now. And there is many advantages for 5G media delivery and all of those. So there is flexibility in signaling. There is the PDU session modification process. You can tailor for multicast. The RAN evolution I showed moves quite quickly. We're talking about 60 kilometers radius now using a single frequency network. There's flexibility in this XMB interface. Particularly the network exposure function and the policy control function, I think they have an increasingly important role in tailoring what the CSP wants for the delivery of media. But obviously there is always some work to do. In BT, we are involved in collaboration projects in my team on this subject, the 5G XCast project, and we are doing also work on the LTE broadcasting from the software-defined radio perspective and the visualization of the core. There is some items on the simplifying that, coming up with APIs that simplify the interface between the content service provider and the network service provider. There's a convergence piece, which is now we're in a position to start discussing it. My colleague John working on that. He's presenting tomorrow. And there is obviously the general challenge of how do you map the quality of service in 5G to the way how the media, the BBC see it. So the BBC sees error second ratio 5%. In 5G we see quality of service indicators and other things. So the two different worlds. But the two worlds are meeting, and my summary is the words you could take. Media delivery is increasingly mobile first, as Jamie said earlier this morning, and 5G is a big opportunity for the network service provider more than the consumer side. So there is a lot of efficiencies can be driven for us as network service providers and content service providers, I think, than what the consumer see 5G is. And the 5G architecture is ready, so let's go and do media delivery in it. Thank you.